All right, guys. Today, I would like to go to something that's really practical. Recursive least square is the basic of parameter adaptation algorithm, and you have learned the core technique over there. Now it's the time to go to something that's being used a lot in practice. A little bit modification from recursive least squares, and I want to show you how and why. So far, we have known if we have a input-output structure uk to yk plus 1, remember my notations, this is really saying that my plant has a one-step delay inside. And I'm just writing in this structure to eliminate this one-step delay and absorb it in this yk plus 1 fashion. So intrinsic one-step delay assumed here. And we know this model is really nothing but just to do the shift operating procedure. So a denominator multiplying with output is going to be equal to numerator with the shift operator notation operating on u of k. And we can derive a predictor kind of structure out of this. The key idea is, I'm just shifting the terms a little bit. BQ, U is the same, and I'm shifting this to the right, minus AQ inverse times YK plus 1, and I add a YK plus 1 on both hands to derive a prediction type of formula. It's the same thing, but this is a prediction structure. All right? And the observation is our assumptions are A is in this kind of structure. So the leading coefficient is 1. We have normalized the coefficient already. Therefore, if we really take a look at this, or even more, take a look at the whole thing that involves the output y, this is really using only information up to time k because of the shift operator here. So therefore, we have the index phi of k instead of k plus 1. All right? So that's the basic modeling technique. Recursive least square utilizes this structure and then says, I'm going to do prediction by replacing the theta vector by its estimate, where the theta hat is defined to include all these coefficients with the hat notation and the index k notation. So just replacing everything here with hat and add a k index inside. And then the recursive least square utilizes this regressor. There's a transpose here. Recursive least square uses a regressor structure that looks like this. The regressor contains y and u. It's a column vector. All right? That's, in a nutshell, how recursive least square in basic adaptation works. Let's take a look at this prediction structure more carefully. This is the a priori prediction. So the a posteriori prediction looks as follows. Y hat k plus 1 is theta hat transpose k plus 1 phi k. And I'm going to start utilizing this equivalent representation more and more in today's lecture. So using this notation, this a posteriori estimation is going to be b hat q. It's updated at time k plus 1. That's the index, right? uk minus a hat Q inverse k plus 1 minus 1 y k plus 1. So the prediction error, epsilon k plus 1, a posteriori again, is yk plus 1 minus y hat k plus 1. And it's going to equal to, just to substitute this inside here, we're going to have yk plus 1 minus, you see, minus minus becomes positive. So yk plus 1 is going to cancel out with this term over here after it multiplies out. Some algebra is going to give you, the result is a hat q inverse k plus 1 yk plus 1 minus b hat all right. This is a quite clean form, and we can put it into a block diagram like this. Input u go into a block diagram, and I want to figure out how, in the end, the a posteriori arrow is going to be formed. Okay? So there are two branches. UK goes through this branch first. And then there's a negative sign. And then we need to generate this term now. This term is something about yk plus 1 going through a hat. And how we can get yk plus 1 from the input u is from here. So this structure both the estimated version of the parameters and the true parameters in this block diagram. So that's the representation, a block diagram representation of the adaptation error. Now, in practice, there will be noises in the measurement, so this is never as clean as what you want. If there are noises in yk, you can see that it's going to go through this filtering structure and generate this error. So intuitively, it's going to create something inconvenient. There are noises in here and then go through this adapting, changing, filtering process. And then it gives the output. So in practice, this part is going to, at least this part from this block diagram, is going to be impacted by noise. That's usually not as desired. All right? We want something that's a little bit cleaner. And the way to do that is, that's the motivation for this new structure that we're going to study today. Observation. Okay? So the observation is as follows. Yk contains noise in practice. And y hat, this is computed This is what we compute. This is what we predict. So this is computed, and we can control. It's less noisy at least. All right? Ideally, if we have asymptotic hyperstability, we have epsilon k plus 1 will go to 0, right? That's the hyperstability, asymptotic hyperstability result. That's going to give us y hat. The a posteriori prediction is going to approximate the true output. So someone looked at this and figured if y hat is computed and potentially be less noisy than the true measurement, why don't we just use y hat in this regressor vector? All right, so let's try to use to construct a new regressor. The U is again the same because this is our control signal. We always have it. And then this y hat is computed. All right? If we do that, then the picture will look like this. So our prediction let's check how our prediction will look like if we adapt this new regressor structure. Prediction is going to become over here, right? So the only thing that's going to, we can look at this one actually. So the different thing is the regressor is going to be replaced with whatever that appears in here as y will be replaced with y hat. So in other words, we are effectively replacing this with the y hat signal. So let's write it more carefully. So it's going to become B UK, and then all right, keep in mind again, if you write this out, it's going to become A1 Q, A1 hat Q inverse okay, so this is going to be exactly something that looks like this. K plus 1. So it is only utilizing information up to time k. And then everything in here you can see on the right-hand side depends only on y hat. So it's a regressor. It is utilizing this regressor here. All right, so let's take a look at what this really means. It means y hat it equals, so let's cancel things out a little. Y hat here, another y hat k plus 1 here. So it is 0 equal to minus A hat operated on yk plus 1 hat. Just out of the formula here. So really, this is saying that y hat is put it into a transfer operator term. The prediction as a transfer operator actually looks very simple. The a posteriori prediction is actually just replacing all the coefficients in B and A by their estimates. Which is slightly different from here. All right? Which is slightly different from here. It doesn't have a clean structure as this. Let's move one step further. Now, the a posteriori prediction, we have done a block diagram before. This is for recursive least squares. Let's take a look at this new predictor structure. It is going to be equal to, it's just yk plus 1 minus y hat. And yk is b over a, this transfer operator. And then the y hat portion, it is just this. So we derived something that's different from the first block diagram. And in this way, you see the subtle difference that we use in the regressor construction actually leads to a more parallel, and if you think about from the noise perspective again. Over there, noise in y is going to go through a hat. Now in here, if this contains noise, it goes straight to here, instead of being again filtered by some complex operation in a hat. All right, so in a block diagram, suppose now in this case, if there is noise, I'm going to add the injection of the noises now. If there's noise in the truth system, there's going to be, so I'm going to draw, the noise is going to be injected, let's say here. In the recursive least square case. And in this case, it's going to be occurring in here. All right? So when there is noise, we can actually expect nicer behavior using this structure because the noise doesn't go through these additional filtering in that stage. And this simple change of regressor vector actually makes a great significance in practical adaptive control and system identification. So, summarizing, when noise exists, this new PAA will turn out to have better convergence. Now, the way that these block diagrams are constructed gives us some ways to name them, to tell the two versions. This block diagram, the noise goes straight at the output side, and then as an arrow go into epsilon k plus 1. So this is called output arrow structure, output arrow method. It is also known as a parallel prediction method because your predictor is entirely in parallel with the true Planck model. And this side, it is not exactly parallel. There is some parallel portion here, but there's also this additional block that is in series with this true Planck model. So this is called series parallel. Predictor. Right? So this is in comparison to the parallel structure. That has an equation, that has an output arrow name. This one also has a name that goes in that spirit. This is called, also known as the equation arrow method. Okay? Because the arrow is written in this way, equation arrow, without the denominator aspect as different from there. Let's focus now on this type of structure, parallel PAA. Let's write out the full PAA formula. Here, we haven't written out everything yet. We only wrote the prediction of y. We haven't written down the theta hat, how it's updated yet. So let's complete the picture now. So let's talk about the PAA summary. With a parallel predictor. The a priori prediction is, the formula is going to be very much like the same. The details are different. So it is still going to be a parameter dilatation gain the difference is why this is going to be different. So let's write it out first. So at every step, we construct this regressive vector, put it into this formula. And in this formula, the adaptation gains are updated by let's introduce now the forgetting factors. All right, so I'm writing the adaptation gain using the inverse form just to save some writing. You can also write out the formula for fk plus 1, which is exactly the same as what we talked about previously. All right. This is the a priori prediction. The a posteriori prediction has also the same structure. So adaptation gain regressive vector times adaptation error in a posteriori form. We have proved stability for the recursive d squares with a constant adaptation gain. Now let's show that this version is also stable. Okay, so in doing this, we're gonna do two things. First, we're gonna expand from our previous stability analysis with only a constant gain to the case where the gain is time varying. So that's one of the new elements here. Second, we are going to see how this change of phi signal will impact our stability proofs. All right, so today let's form the block diagram first. Let's form the feed-forward feedback linear in feedback connection with a nonlinear block diagram first. Let's take a look at the adaptation error. So next, form the feedback block diagram. Remember what we did in the previous case. We first derived something that depends on theta tilde. We focus on the arrows. So let's do the same here. Let's see how theta tilde, the estimation vector, the error of the estimation vector will look like. All right, so this was defined as theta hat k plus 1 minus theta. And if we plug in all these, we will see that it's the same formula. So it is theta tilde k plus fk phi k epsilon k. So that's easy. Now let's express epsilon in the form of theta tilde as the next step. We know for the Planck model, we have this. This is the Planck model. And the predictor formula over there is so we got to do some subtraction to create this epsilon k plus 1 signal. So let's try to do, again, something using the principle of add and subtract terms. All right? So if I add and subtract, I'm going to be able to do something like this. Let's try. Let's try this. I know epsilon k plus 1 is yk plus 1 minus y hat. So let's subtract a term involving y hat. And I need to add it back. So I haven't done anything new to the left-hand side. So the right-hand side should be the same. And if I do that, I will be able to now see that I can combine the first two terms to generate epsilon k plus 1. And then I'm going to shift this term to the right. All right. Now let's put in the second equation. Let's do this. So the right-hand side is going to be equal to this minus a q inverse y hat k plus 1. I'm going to add a hat k plus 1 y hat k plus 1. I add this term and I subtract this term. And it should be the same thing. But once I do that, I can see that I can have b minus b hat, which contains the difference of the predictor, which contains theta hat, some part of theta hat. And the same thing here. I have y hat, so grouping these two will give me another portion of the theta tilde vector. Okay? So this is very close to the final result. Let's group them in a way. I am going to put a hat. I'm going to consider the y hat signal first. This is these two terms minus All right? So now the formula will become, this is going to be very much similar to the theta tilde vector again. If we consider, so A is 1 plus A1, if we write it out. This is the A hat minus that's the first part. And if we work on this a little bit, you can see that this is nothing but A1 tilde, the difference between A1 hat and A1, Y hat K. So I'm doing two things. First, I am subtracting A hat with A1, subtract A with A hat. Second, I am absorbing this shift operator and multiply this with Y hat K plus 1 to generate Y hat K, plus A2 tilde K plus 1 Y hat K minus 1 plus A3 tilde K plus 1 Y hat K minus 2, etc. That's the first part. For the second part, it's similar thing, minus B0 tilde UK plus B1 tilde. So essentially the way, after you do this 1 or 2 times, you will notice the way to see this is nothing but, if this is, both terms are about B, then B hat minus B, it's essentially a polynomial with coefficients just look like replacing every B with B tilde signal, B tilde K plus 1 inside. Same thing here, okay? This is exactly the predictor formula, looking like the predictor formula. If we now put it into a vector form. So this equals let's put it into a vector form. I'm going to write the parameter vector first. A1, I'm going to do A1. Yes, I'm going to do A1 tilde and then B0. This row vector multiplying with this column vector. So I have A1 tilde multiplying with Y hat. I'm going to do this. And then the B tilde signals is going to be multiplied with negative UK. Okay? So what can we say about these two? I know this first one, this is really nothing but our parameter vector difference. Okay, so this is just replace A1, A2, etc. with A1 tilde add a time index to it. And then this is, you see, y hat and u here. This is really nothing but the negative of our regressor vector if you compare it with the first line on the left-hand side. So this is really negative theta tilde k plus 1 transpose times phi k. And then once you see this step, you can immediately write out the block diagram. Because, recall, what we did last time, in pure recursive least squares, what do we have? In the series parallel predictor, now we can call this, we can use the official name now. In that, if you take a look at your notes, the arrow is negative theta tilde k plus 1 phi k. In the sense that the block diagram, the feed-forward path is exactly just 1. All right, that's the series parallel predictor from previous lectures. And the only thing that changes in this way is there's something else hanging here. So the linear block is going to change a little. Everything else will be the same. So we'll come back to the block next time.